Hello everyone. So in this thermal engineering video series, now I am going to discuss about the topic ethanol blending in the fuels. So these are the presentation overview. I am going to discuss ethanol blending in fuels introduction, common blend ratios and the production pathways such as first generation, second generation and advanced methods, and properties and performance of ethanol blending in fuels, advantages, and we are going to discuss about some challenges faced and stakeholder challenges, global implementation, some examples Brazil such as mandatory for 27% blend and flex fuel focus, and USA renewable fuel standard E10 standards, and India E20 initiative, that means target 20% by the 2025, and some future outlooks. In this way I am going to discuss about this ethanol blending in the fuels topic. So ethanol, the chemical formula is C2H5OH, is a renewable alcohol based fuel produced from the biomass fermentation. When blended with the petrol, it reduces the fossil fuel dependence whilst lowering the greenhouse gas emissions. So common blend ratios are E10, that means 10% of ethanol, and E15, 15% of ethanol, and E18, 85%, and E100, that is called pure ethanol. Most modern vehicles accommodated the ratio of 10% ethanol, it is called E10, without any modifications. Ethanol blending represents a practical bridge between the conventional fossil fuels and the fully renewable energy system in the transportation system. So production pathway and the feedstock sources are first generation and second generation and advanced methods. In the first generation, the ethanol blending is produced from the food crops like maize, sugarcane and wheat through the fermentation process and distillation process. In second generation, the ethanol is derived from the lignocellulosic biomass, including the agricultural waste, wood chips and non-food plant materials. In advanced method, it is the emerging technologies using algae, synthetic biology and waste to ethanol conversion process. So these are some of the methods. In these methods, the ethanol is derived. Some fuel property and performance characteristics are the octane rating in the range of 109, and the value of is compared to the 91 to 90% for the standard petrol, and 66% of energy density relative to the petrol by the volume, and 35% of oxygen content by weight in the pure ethanol. Some of the key advantages are higher octane rating enables the increased compression ratios, a cleaner combustion with reduced particulate emissions, and lower vapor pressure improves the cold start performance and excellent anti-knock properties. And some of the key challenges are lower energy content requires the 30% more fuel for the equivalent range, and hydroscopic nature causes the water absorption issues. These are some of the challenges. And combustion chemistry and engine performance by using the ethanol blending. Ethanol's molecular oxygen content 35% weight promotes the more complete combustion compared to pure hydrocarbons. The combustion reactions equations is like C2H5OH, that is ethanol plus 3 oxygen, 3 O2. It gives the 2 molecules of carbon dioxide, 2 CO2 plus 3 molecules of water, 3 H2O, and releases the energy. This stoichiometric combustion produces the higher flame speed and cooler intake charges due to the ethanol's high heat of vaporization in the range of 841 kJ per kilogram versus the 350 kJ per kilogram for the petrol. The cooling effect allows for more aggressive ignition timing and higher compression ratio without the knock, potentially increasing the thermal efficiency by 3 to 5% compared than the without blending. In design thinking stages, the first stage is empathize. So understanding the stakeholder challenges in ethanol adoption, vehicle owners, fuel producers and environmental advocates, they are all the stakeholders. In the concern of vehicle owners, the concerns about engine compatibility, fuel efficiency, reduction, potential corrosion in the other vehicles and viability in filling stations. Infrastructure investment requirements and blending the logistic storage challenges due to the ethanol's hydroscopic nature and quickly control complexity. In the term of environmental advocates, land use implication and water consumption are the major sources. So some of the real world applications and the implementations in Brazil's ethanol program since 1975, Brazil has implemented mandatory ethanol blending of 27%. Currently, flex fuel vehicles constitute the 90% of the new car sales, demonstrating the large scale viability. Followed by US renewable fuel standard that mandates 36 billion gallons of renewable fuel by 2022. The ethanol blending of 10% is called as E10 is standard nationwide with E15 and E85% infrastructure expanding the rapidly. In India's ethanol 20% initiative target of 20% of ethanol blending by 2025 to reduce the oil imports. Focus on sugarcane and the grain-based ethanol production facilities. These are the some initiatives taken by the governments of various government. So followed by the emphasized stage, the another stage is prototype, developing the optimized ethanol blend formulations by the way of blend ratio selection, additive integration, and engine testing protocol and durability assessment. So this is the environmental impact and the emission analysis of carbon dioxide, carbon monoxide, and carbon HC and NOx emissions. In this comparison, the carbon dioxide emission is high range around 180. So some of the key takeaways and future outlooks are technical feasibilities and material consideration and performance trade-offs, and finally the future innovations. So the second generation cellulosic ethanol advanced engine designs optimized for the high ethanol blends and integrated biorefinery concept will enhance the sustainability. Some of the engineering challenges are develop the flex fuel engine technologies that maximize the efficiency across the entire ethanol blend spectrum while maintaining the durability and the emission compliance. So thank you for watching.